to the 7th session on electrolytic conductance. In this session, we will be dealing with applications of conductance measurements. Measurement of conductance values will give us a very large amount of information regarding the electrolytes, both strong as well as weak electrolytes. And among this, first we will be dealing with the application of Kohlrausch's law. Kohlrausch's law, as you all know, it is a law which is used for determination of molar conductance at infinite dilution of especially weak electrolytes, because molar conductance at infinite dilution will be equal to sum of molar conductance of the cation as well as the molar conductance of the anion. Based on this, we will see some of the applications. First one is calculation of limiting molar conductivity of weak electrolyte. As you have seen, in a graphical method, you can never find a limiting molar conductivity of a weak electrolyte, because the graph goes parallel to the molar conductance axis, and therefore, here we apply Kohlrausch's law. Now, suppose you are supposed to find the lambda 0 m of acetic acid. Suppose if it is plotted and we think that we can extrapolate, the graph goes parallel to the lambda m axis molar, and here it is the root of concentration. So, as it goes parallel, it is difficult to find out the lambda 0 m value for acetic acid. This is a weak electrolyte, but for strong electrolytes the case is different. Now, what we do in this is, we will find the lambda 0 value of a strong electrolyte which contains the ions, that is, we have from acetic acid. Acetic acid is supposed to split as acetate ion and H plus ions. Okay. So, we are going to take strong electrolytes which contain the acetate ion and H plus ion. So, in this case, I can take this as sodium acetate. So, from this electrolyte we will be getting the acetate ion. Now, add the lambda 0 value for an electrolyte that contains H plus ion, again that should be a strong electrolyte, let that be HCl. Now, when we do this, we have two additional ions involved, that is Na plus and Cl minus. We do not need these. So, what we do is, we take another electrolyte combining these two, and that should also be a strong electrolyte, and that will be a sodium chloride. Okay. So, I sum up these two, which contains, they should be strong electrolyte and contains an acetate ion, and another one which contains H plus ion and a chloride ion along with it, so that it makes a strong electrolyte, and the additional ions are combined to get another strong electrolyte which is being subtracted. Now, let us see whether it is correct. Lambda 0 of sodium acetate can be considered as lambda 0 of acetate ion plus lambda 0 of sodium ion. In case of HCl, that will be lambda 0 of HCl, sorry, lambda 0 of H plus plus lambda 0 of Cl minus. From these two values, we have to subtract the lambda 0 of Na plus, lambda 0 of Na plus minus lambda 0 of Cl minus, because minus is common for both. Now, cancelling the common terms. See, here we have plus lambda Na plus, this is minus lambda Na plus, this is plus lambda 0 Cl minus, and this is minus lambda 0 NaCl, and finally, you get this will be equal to lambda 0 of acetate ion plus lambda 0 of H plus, and that is what we call it as lambda 0 of acetic acid. So, if you take these, you can find out the molar conductance at infinite dilution of a weak acid, that is acetic acid. So, for finding out the molar conductance of a weak acid, we are choosing some strong electrolytes, and these values they can be determined graphically, all these lambda 0 values, because they are all strong electrolytes. Okay. So, that is one of the method. Let us see one more example in which I am going to take a base, that is ammonium hydroxide. This is a weak base. Now, if we have to find out lambda 0 of ammonium hydroxide, I take an electrolyte which contains ammonium ion, and that should be a strong electrolyte. So, I am taking it as ammonium chloride plus another strong electrolyte which contains OH minus ions. So, lambda 0 of, I can put it as potassium hydroxide which contains OH minus ions. Now, the additional ions have to be subtracted. So, minus lambda 0 of HCl. Again, if you split up, you will finally end up in lambda 0 of NH4 plus lambda 0 of OH minus, and that will give you the lambda 0 of NH4 OH. Now, let us see the problem. Here, the molar ionic conductance of infinite dilution of magnesium and chloride ions are 106 and 76.25 Siemens centimeter raised to minus 2 and mole raised to minus 1. Siemens stands for ohm inverse at a certain temperature. Calculate the molar conductance at infinite dilution of magnesium chloride at that temperature. It is a direct question of Karl-Rausch's law. First of all, what we have to do is, you take magnesium chloride and first write down its ionization, Mg2 plus 2Cl minus. Okay. So, you should take care, that is, here we will be having 2 chloride ions, and therefore, lambda 0 of MgCl2 will be equal to lambda 0 of Mg2 plus, that is only one ion, but in the case of chloride you will be having 2, that is lambda 0 of Cl minus, 2 into lambda 0 of Cl minus, because from one MgCl molecule you are going to get 2 chloride ions. Now, you can substitute the values. Lambda 0 of Mg2 plus is equal to 106 plus 2 into 76.25, because you have 2 chloride ions, and final answer will be 258.5 Siemens centimeter square mole inverse. Okay. So, whenever an electrolyte is given, first write down how it is being ionized and then write the Karl-Rausch's equation and find out the value. Now, this is another question. The molar conductance at infinite dilution of potassium acetate, hydrochloric acid and potassium chloride are given here. Okay. And you are supposed to find out the molar conductance at infinite dilution of acetic acid. We know that lambda 0 of acetic acid should be equal to lambda 0 of an electrolyte, strong electrolyte with acetate, and here it is potassium acetate. So, I can put it as CH3COOK. To that you have to add a strong electrolyte which contains the H plus ion, and that electrolyte is hydrochloric acid. So, that is lambda 0 of HCl, and the additional ions are K plus and Cl minus, and for sure you can see that is here the value of potassium chloride is given minus KCl. So, you have to write according to the data provided. Lambda 0 of potassium acetate is 95.6 and that of hydrochloric acid is 379.4 and that of potassium chloride that you have to subtract is 130.1, and the final answer you will be getting it as, you add up 95.6, 379.4, 10 carry over 15, carry over on 17, carry over 1 4, 0.0 minus 130.5, that will be 9, 4, 4, 3. That will be equal to 344.9 Siemens centimeter square per mole. Okay. Next, we have to see the calculation of degree of dissociation of weak electrolytes. We know that weak electrolytes, they get only partially ionized in solution, and at a particular concentration, lambda m will be proportional to number of ions at that concentration, at concentration C, and lambda 0 m will be proportional to total number of ions, because all ions are ionized at lambda 0, and therefore, the ratio will give you alpha, the degree of dissociation. Now, this can be determined experimentally, that is lambda m is determined experimentally, while lambda 0 m is calculated using our Karl-Roche's law, that is we have been doing so far, and substituting these values you can find out the degree of dissociation of a weak electrolyte. Now, let us go for a problem. Here the limiting molar conductivities of ammonium chloride, sodium hydroxide and NaCl are 129.8, 217.4 and 108.9 ohm inverse centimeter square mole inverse respectively at 298 Kelvin. The electrolytic conductivity of 0.01 molar solution of ammonium hydroxide at 298 Kelvin is 9.33 into 10 to the power minus 5 ohm inverse centimeter. Calculate the degree of dissociation of ammonium hydroxide at this dilution. So, first we have to find out lambda 0 m, sorry, it is not lambda 0 m, lambda m. We have to find out lambda m and also lambda 0 m. Now, lambda 0 m, as you all know, you will be doing using Karl-Roche's law, and lambda 0 m has to be determined for ammonium hydroxide. So, that will be lambda 0 m of ammonium hydroxide, which is equal to lambda 0 of ammonium chloride, because that is the one which is given, plus lambda 0 of NaOH, that is another electrolyte. So, we have ammonium and hydroxide minus lambda 0 of NaCl, that is equal to 129 ammonium chloride 129.8 plus 217.4 minus NaCl, that is 108.9, and from this you will get the answer as 238.3 ohm inverse or Siemens centimeter square mole inverse. So, that is obtained using Karl-Roche's law. Next is they have given the conductivity of 0.01, that is conductivity means there is a specific conductance. So, from that you have to calculate lambda m is equal to kappa into 1000 by m. Kappa is 9.33 into 10 to the power minus 5 into 1000, whole divided by molarity 0.01. You calculate this value, and with this we are going to find out the value of alpha. Alpha is equal to lambda m, that is 238.3 divided by 9.33 into 10 to the power minus 5 into 1000 into the denominator goes to the numerator 0.01, and you get the answer as 0.03915, and that is the value of alpha. So, lambda m is also calculated, lambda 0 m is also calculated, and you are finding out the alpha, the value of degree of dissociation. Next is determination of solubilities and solubility product. We know that lambda m is equal to kappa into 1000 by m. For sparingly soluble salts, we can put that the concentration m can be taken as the solubility. S stands for solubility. Okay. Now, I can substitute this as S, m can be substituted as S. Now, being sparingly soluble, lambda m means it is a very dilute solution, and therefore, it can be taken as lambda 0 m itself. So, substituting all this, I can put it as lambda 0 m is equal to kappa into 1000 by S, or S is equal to kappa into 1000 by lambda 0 m. Here lambda 0 m is derived from Colruysch's law. Kappa is measured and solubility of the electrolyte can be determined, especially of sparingly soluble salt. Here we have a problem based on it, that is conductivity of a saturated solution of AgCl at 298 Kelvin. After subtracting the conductivity of water, that is exactly of AgCl alone, is equal to 2.28 into 10 to the power minus 6 ohm inverse centimeter inverse. Calculate the solubility of AgCl in water at 298 Kelvin, given molar ionic conductances of Ag plus and Cl minus ions at infinite dilutions are 61.94 and 76.36 ohm inverse centimeter square per mole. You have to find out lambda 0 as well as kappa. So, kappa is given is equal to 2.28 into 10 to the power minus 6 ohm inverse centimeter inverse. So, kappa is given, but you have no idea about what is lambda 0 m. It is not given, but you can find out using Colruysch's law, and that is of AgCl, where lambda 0 of Ag plus lambda 0 of Cl minus can give you the value. Lambda 0 of Ag plus is equal to 61.94 plus that of Cl minus 76.36, and you will get the value as 238.3 ohm inverse centimeter square mole inverse. Now, you can do that solubility. Solubility is equal to, we were using that expression, that is solubility is kappa into 1000 by lambda 0 m is equal to kappa into 1000 by lambda 0 m, which is equal to kappa is equal to 2.28 into 10 to the power minus 6 into 1000 divided by 238.3, and you will get the answer as solubility is equal to 1.649 to 10 to the power minus 5 moles per liter. So, you can determine the solubility of insoluble salt. So, in this session, we have been dealing with Colruysch's law, its application. Colruysch's law, which we have studied some classes before. Here, we are applying Colruysch's law and determine many of the conductance values. Here, we calculated the lambda 0 m or molar conductance at infinite dilution of a weak electrolyte applying Kalrausch's law. Second is we calculated the degree of dissociation of weak electrolytes, and third one we have been seeing, that is we found the solubilities and also solubility product of sparingly soluble salt. Thank you.